Energy, as Richard Feynman described it, does not behave like a physical object that can be touched, stored in a box, or poured from one place to another. This idea is often difficult to accept because human intuition prefers concrete images. We imagine energy as something flowing, something moving invisibly through wires, fuels bodies, or machines. Yet Feynman deliberately challenged this intuition by stating a simple but unsettling truth: energy is an abstract concept, a number we calculate, not a substance that exists on its own. This statement does not weaken the importance of energy. Instead, it reveals its extraordinary power as a tool for understanding nature. When physicists talk about energy, they are not pointing to a single physical entity. They are talking about a system of rules that allows them to track how nature changes. Energy is a bookkeeping device, much like financial accounting. In finance, money itself is not tied to a specific object. A dollar can be cash, a digital number in a bank account, or a credit balance. What matters is that the total amount is conserved when properly tracked. In physics, energy plays a similar role. It takes different forms depending on the situation, but the total remains consistent when all contributions are counted correctly. Feynman often illustrated this idea with simple analogies because simplicity exposes truth. He imagined a child playing with blocks. Each day, the child starts with a fixed number of blocks. During play, some blocks are stacked, some are hidden under the rug, some are placed in a toy box, and others are left outside. At the end of the day, the parent counts the blocks and always finds the same total, even though their locations and arrangements have changed. The blocks represent energy, and the various hiding places represent different energy forms. The point of the analogy is not the blocks themselves, but the act of counting. Energy is the count that never changes, even when appearances suggest otherwise. This accounting perspective explains why energy feels so elusive. Unlike mass or charge, energy does not have a single physical manifestation. Mass is something objects possess. Charge can be positive or negative and produces observable forces. Energy, on the other hand, is inferred from motion, position, temperature, radiation, and interactions. We never observe energy directly, we observe changes, and energy is the numerical quantity that remains consistent through those changes. Historically, this abstract view of energy emerged gradually. Early scientists spoke of vis viva, or living force, believing motion itself carried a substance-like quality. Later, heat was thought to be a fluid called caloric. These ideas eventually failed because they could not explain why heat could be created by friction or why motion could disappear and reappear in different forms. The modern concept of energy unified these observations by abandoning the idea of a physical fluid and replacing it with a conserved quantity. Feynman emphasized that this abstraction is not a weakness of physics, but its greatest strength. Because energy is defined mathematically, it applies universally. Whether analyzing a falling apple, a moving planet, a vibrating molecule, or a nuclear reaction, the same accounting principle holds. The equations may differ, the forms may vary, but the total energy remains constant. This universality is what makes energy such a powerful concept. One of the most striking aspects of energy as an accounting concept is that it often hides itself. When a moving car brakes, the visible motion disappears. To an untrained observer, the energy seems gone, but physics insists that it must be accounted for. The car's kinetic energy transforms into heat in the brakes, the tires, the road, and the surrounding air. On a microscopic level, atoms vibrate more rapidly, increasing thermal motion. The energy was never destroyed, it simply shifted into less obvious forms. This hidden nature of energy forces scientists to look deeper. It pushes inquiry beyond surface appearances into microscopic and even subatomic levels. When energy seems to vanish, it is a signal that something is happening beneath the surface. In this way, energy accounting has driven major discoveries, from thermodynamics to quantum mechanics. The insistence that energy must always balance has revealed entire worlds of invisible processes. Feynman was careful to point out that even though energy is abstract, it is not arbitrary. The rules governing energy accounting are precise and experimentally verified. Every known interaction obeys energy conservation. Even in the strange realm of quantum physics, where particles behave like waves and probabilities replace certainties, energy remains strictly conserved. The forms become quantized, but the accounting remains exact. This precision is what separates energy from philosophical abstractions. Energy is not an idea invented for convenience alone. It is an idea forced upon us by nature. Experiments demand it. Measurements confirm it. Predictions based on energy accounting consistently match reality with astonishing accuracy. Planes fly, power plants operate, and technologies function because engineers trust energy calculations more than intuition. Feynman's approach also reshapes how we think about cause and effect. Instead of asking where energy comes from or where it goes, physics asks how energy transforms. This shift removes confusion. When a battery powers a device, energy is not oozed up in the sense of disappearing. Chemical energy becomes electrical energy, which becomes light, sound, or heat. The battery loses stored energy because it has been transferred and transformed, not destroyed. Understanding energy as an accounting concept also dissolves many common misconceptions. For example, people often believe that energy is something living beings have in a special way. In reality, biological energy obeys the same rules as mechanical or electrical energy. The food we eat contains chemical energy, which our bodies transform into motion, heat, and biological processes. Life does not break the rules of energy, it follows them with remarkable efficiency. On a deeper level, this perspective reveals something profound about reality. The universe appears to be governed not by substances alone, but by relationships and balances. Energy represents a balance that never fails. It is a silent rule operating behind every visible change. Objects move, systems evolve, structures form and decay, but the accounting remains intact. Feynman's explanation invites humility. If one of the most fundamental concepts in physics is not a tangible thing, then reality is not limited to what we can see or touch. The deepest laws of nature may be mathematical relationships rather than physical objects. Energy exemplifies this idea. It exists as a rule, a consistency, a constraint on how the universe can behave. This realization also explains why energy unifies so many branches of physics. Mechanics, thermodynamics, electromagnetism, relativity, and quantum theory all rely on energy accounting. Each field describes different phenomena, but all agree on this fundamental principle. The language changes, the equations evolve, but the concept of energy binds them together. Feynman did not present energy as a mystical force or a poetic metaphor. He presented it as an honest admission of how science works. We do not always know what things are, in a philosophical sense. What we know is how they behave and how they relate to one another. Energy is one of those relationships, a number that nature refuses to change. In the end, the abstract nature of energy makes it more real, not less. Its reality lies in its reliability. It never fails, it never lies. It quietly governs every transformation in the universe. By understanding energy as an accounting concept, we gain not only a clearer view of physics, but a deeper appreciation for the hidden order underlying all change. Energy, when viewed through the lens Richard Feynman encouraged, becomes even more fascinating once we move beyond simple examples and begin to see how this abstract accounting concept operates across increasingly complex systems. The idea that energy is just a number does not make it trivial, it makes it universal. That number follows the universe everywhere, from the smallest vibration of an atom to the motion of entire galaxies, and it never breaks its own rules. One of the most important consequences of energy being an accounting concept is that it allows prediction. If energy were a substance with vague behavior, physics would be unreliable. Instead, because energy is defined mathematically, scientists can calculate future outcomes with extraordinary accuracy. When engineers design a bridge, they calculate how energy from wind, traffic, and gravity will flow through the structure. When astrophysicists study stars, they calculate how energy produced in the core will travel outward as radiation. In every case, the same principle applies: energy in must equal energy out, once all forms are included. Feynman emphasized that this predictive power does not come from knowing what energy is, but from knowing how it behaves. This distinction is crucial. Physics does not require metaphysical certainty to be effective. It requires consistent rules. Energy provides those rules by acting as a constraint on all physical processes. Nature is free to behave in astonishingly diverse ways, but it is not free to violate energy accounting. As systems grow more complex, energy accounting becomes more subtle. In simple mechanical systems, energy appears as motion or position. In thermal systems, it appears as random microscopic motion. In electromagnetic systems, it appears in fields and radiation. In nuclear processes, it appears as changes in mass itself. Each time physics expanded into a new domain, the definition of energy expanded with it, incorporating new terms while preserving the total balance. This adaptability is one of energy's most remarkable features. When Einstein showed that mass and energy are equivalent, it was not a rejection of energy conservation, but a refinement of it. Suddenly, mass became another way energy could hide. Objects at rest contain enormous amounts of energy simply by existing. This insight explained nuclear reactions, stellar fusion, and the long-lasting energy output of stars. The accounting still worked, it just required a broader view. Feynman's explanation also highlights why energy sometimes feels unintuitive. Human senses evolved to deal with visible motion and direct forces, not abstract balances. Heat, for example, feels different from motion, even though they are both expressions of energy. A hot object does not move as a whole, yet its atoms vibrate intensely. Energy accounting reveals that these vibrations carry just as much physical significance as visible motion, even if our senses cannot detect it directly. This disconnect between intuition and reality is especially evident in modern technology. When electricity flows through a circuit, electrons drift slowly, yet energy is transferred rapidly. The energy does not travel as particles moving from one end to the other, but through electromagnetic interactions that redistribute energy throughout the system. Thinking of energy as a substance moving along wires leads to confusion. Thinking of it as an accounting quantity clarifies what is really happening. Feynman also stressed that energy conservation is deeply connected to symmetry in nature. Although he avoided unnecessary philosophical language, the underlying idea is profound: the laws of physics do not change over time, and because of that, energy is conserved. This connection reveals that energy is not an isolated rule, but part of a larger structure governing reality. The universe's consistency gives rise to energy's reliability. In chaotic systems, energy accounting becomes even more important. Weather patterns, turbulent fluids, and biological systems appear unpredictable, yet they still obey energy conservation. Even when precise outcomes cannot be forecast, energy constraints limit what is possible. Hurricanes draw energy from warm oceans. Ecosystems distribute energy through food chains. Life itself is a complex flow of energy transformations, not an exception to physical law. This perspective reshapes how we think about efficiency and waste. When energy is lost, it is not destroyed but dispersed into forms that are harder to use. A machine that produces heat is not losing energy, it is converting useful energy into less organized forms. This realization lies at the heart of thermodynamics and explains why perpetual motion machines are impossible. The accounting always balances, but usefulness declines as energy spreads out. Feynman's approach strips away mysticism while preserving wonder. Energy does not need to be a mysterious force to be extraordinary. Its power lies in its quiet consistency. No matter how advanced physics becomes, no matter how strange new discoveries appear, energy conservation remains untouched. New theories do not discard it, they deepen it. As physics pushed into quantum territory, the accounting concept of energy survived yet again. Particles can appear and disappear, borrow energy briefly within strict limits, and behave in probabilistic ways, but the overall balance is never broken. Even the vacuum, once thought empty, contains fluctuating energy that must be accounted for. What appears as nothing still participates in the universal bookkeeping. This reveals the final depth of Feynman's insight. Energy is not a thing that drives the universe, it is a rule the universe obeys. It is a boundary condition on reality itself. Everything that happens must respect it. Every change, every interaction, every transformation fits within its accounting framework. Understanding energy in this way transforms how we see the world. It teaches us that reality is not built only from objects and forces, but from constraints and relationships. Energy is one of the most important of those relationships. It binds together motion and heat, matter and light, life and stars, into a single coherent picture. In the end, Feynman's explanation leaves us with a powerful lesson about knowledge itself. Science does not always answer questions by revealing the essence of things. Sometimes it answers by revealing the rules that never fail. Energy is one of those rules, a silent agreement the universe never breaks. By accepting energy as an abstract accounting concept, we do not diminish its importance. We recognize its true, universal strength. Energy conservation, as Richard Feynman explained it, is not merely a scientific rule, but a deep statement about how nature behaves. It tells us that beneath all visible change, beneath motion, heat, light, sound, and even life itself, there is a balance that never breaks. This balance is not obvious to the senses. In fact, most of the time it appears to be violated. Objects stop moving, machines slow down, fuel burns away, and energy seems to disappear. Yet physics insists that this disappearance is an illusion created by incomplete observation. Feynman stressed that conservation of energy does not mean energy stays in the same form. On the contrary, energy is constantly changing its appearance. What remains unchanged is the total amount when all forms are included. This is why conservation of energy often feels mysterious. Nature hides energy extremely well, distributing it into places where human intuition does not naturally look. Consider something as simple as a moving object sliding across the floor. At first, it has visible motion, something easy to associate with energy. As it slows down and eventually stops, the motion vanishes. To everyday thinking, the energy seems gone. But physics refuses to accept that conclusion. Instead, it demands that the energy be found. Careful analysis shows that the energy has transformed into microscopic motion within the floor and the object itself. Atoms vibrate slightly faster. The temperature rises, often by an amount too small to notice. The energy is still there, but it is hidden in forms spread across countless particles. This hiding of energy is one of the most important ideas Feynman wanted people to understand. Energy rarely disappears dramatically. It leaks into subtle, distributed forms. Sound waves fade into random molecular motion. Mechanical motion dissolves into heat. Electrical energy radiates away as electromagnetic waves. The universe is constantly converting organized energy into disorganized energy, not destroying it. The need to account for hidden energy drove major scientific advances. Early scientists noticed that friction could produce heat seemingly from nothing. This observation once supported the idea that heat was a fluid stored inside objects. But experiments showed that heat could be generated endlessly through motion, undermining that model. The conservation of energy resolved the puzzle by revealing that motion was being converted into heat. Nothing was created, nothing was destroyed. Feynman emphasized that conservation of energy is not derived from one experiment, but from countless confirmations across different fields. It holds for falling objects, chemical reactions, electrical circuits, nuclear processes, and cosmic events. Every time physicists thought they had found an exception, deeper investigation revealed hidden energy at work. This pattern built extraordinary confidence in the principle. One of the most powerful aspects of energy conservation is that it works even when causes are complex or unknown. Scientists do not need to understand every microscopic detail of a process to apply energy accounting. If the initial and final energies are known, much can be predicted. This is why energy is so valuable in engineering and science. It provides certainty in a world of complexity. Feynman also made clear that energy conservation does not depend on human perception. The universe does not care whether energy is visible, useful, or convenient. It only cares that the balance holds. When energy spreads into many tiny motions, it becomes harder to recover for practical purposes, but it remains fully present. This distinction explains why machines wear out and why perpetual motion devices are impossible. Energy conservation allows endless transformation, but thermodynamics limits how much of that energy can be harnessed again. Hidden energy becomes even more striking in modern physics. In electrical systems, for example, energy transfer does not match the movement of particles. Electrons drift slowly through wires, yet energy flows almost instantly. The energy is carried by electromagnetic fields surrounding the conductors, not by electrons traveling from one end to the other. Without understanding energy conservation and hidden forms, this behavior seems paradoxical. In chemical reactions, energy is stored in bonds between atoms. These bonds are invisible, yet they determine whether a reaction releases energy or absorbs it. When fuel burns, chemical energy becomes heat and light. The atoms rearrange, and the difference in energy between the old bonds and the new ones appears as released energy. Nothing vanishes. The accounting balances perfectly. Feynman's explanation also clarifies why energy conservation applies even in violent or dramatic events. Explosions feel destructive, yet they are simply rapid redistributions of energy. Stored energy is released quickly into motion, heat, light, and sound. The chaos does not break the rules, it merely spreads energy more rapidly and more widely. In nuclear reactions, hidden energy reaches an extreme. A tiny amount of mass converts into enormous energy. Before Einstein, this energy seemed to appear from nowhere. After mass-energy equivalence, it became clear that mass itself is a deeply hidden form of energy. Objects at rest contain vast energy simply by existing. This realization expanded the accounting system, but did not change its principle. Energy conservation survived intact, stronger than ever. Feynman took particular care to avoid presenting energy conservation as mystical. It is not a magical law imposed from outside reality. It is an observed regularity, tested repeatedly and never found wanting. Its reliability suggests something profound about the universe. Despite its complexity, it operates under strict constraints. This constraint is what allows stability. Atoms do not randomly collapse. Stars shine for billions of years. Planets follow predictable paths. All of this depends on energy being conserved. Without it, the universe would be chaotic beyond comprehension. There would be no reliable processes, no persistent structures, no life. The idea of hidden energy also reshapes how we think about waste. When energy is wasted, it is not destroyed but dispersed. A light bulb produces heat because some electrical energy becomes random atomic motion instead of visible light. The heat still counts in the energy balance. From the universe's perspective, nothing went wrong. From a human perspective, the energy became less useful. Feynman's explanation encourages a deeper appreciation of nature's honesty. The universe never cheats. It never loses track of energy. If something seems to vanish, it is because our measurement or understanding is incomplete. This attitude has guided generations of physicists to search for deeper explanations rather than accepting apparent violations. At its core, conservation of energy teaches patience and humility. It reminds us that appearances can deceive, but rules endure. Motion can stop, heat can spread, light can fade, but energy remains hidden in forms that require careful thinking to uncover. This understanding changes how we see every process around us. Nothing truly disappears. Everything transforms. Every action leaves an energetic trace woven into the fabric of the universe. And through all these transformations, the accounting remains exact, silent, and unbroken. As the idea of hidden energy deepens, conservation of energy begins to reveal its most powerful role. It acts as a universal referee that nature never argues with. No matter how strange a phenomenon appears, no matter how unfamiliar the scale or mechanism, energy conservation quietly constrains what can and cannot happen. This is why Feynman treated it not as a mechanical rule, but as a guiding principle that exposes deeper layers of reality whenever confusion arises. One of the most revealing examples of hidden energy appears in gravitational systems. When an object falls, it speeds up, gaining kinetic energy. When it rises, it slows down, seemingly losing energy. The key is that gravity stores energy in position. This stored energy is invisible, yet it is real in the accounting sense. Two objects separated by distance contain energy simply because of their arrangement in space. Nothing moves, nothing heats up, yet energy exists within the configuration itself. This challenges the instinct that energy must involve activity. Sometimes energy is present purely as potential. Feynman emphasized that potential energy is not located in the object alone, nor in space by itself, but in the relationship between objects. This reinforces the abstract nature of energy. It does not belong to things, it belongs to systems. Change the system, and the energy changes, even if no object visibly transforms. This relational character is one of the reasons energy conservation works so universally. Hidden energy also plays a crucial role in waves. A sound wave moving through air carries energy, even though air molecules barely travel from their original positions. They simply oscillate back and forth. The energy is stored partly in motion and partly in compression. When the sound fades, the organized motion dissolves into random thermal motion. The wave disappears, but the energy remains, now hidden as heat. Light behaves in a similar way. A beam of light can travel through empty space for billions of years carrying energy without mass or material substance. When it strikes an object, its energy transforms into heat or triggers chemical reactions. The disappearance of the light does not mean the disappearance of energy. Once again, the accounting balances even across cosmic distances. In electrical phenomena, energy conservation reveals its subtlety most clearly. When a switch is flipped, a light turns on almost instantly, even though electrons move slowly. The energy travels through electromagnetic fields that rearrange themselves throughout the circuit. Without understanding hidden energy in fields, this behavior seems impossible. With energy accounting, it becomes expected. Feynman also pointed out that energy conservation applies even when time itself behaves strangely. In quantum mechanics, particles can appear to violate classical rules, tunneling through barriers or briefly borrowing energy. Yet these apparent violations always obey deeper accounting constraints. The universe allows temporary fluctuations, but it never allows permanent imbalance. Over time, the books always balance. This principle forced physicists to accept that energy sometimes exists in places we cannot directly observe. The quantum vacuum, once thought empty, is filled with fluctuating energy. These fluctuations have measurable effects, influencing particle behavior and cosmic expansion. What was once nothing turned out to be energetically active. The conservation rule remained unchanged, only our understanding expanded. Feynman's explanation also reshapes how we think about causality. Energy conservation does not tell us why something happens, but it tells us what must be true if it does. If energy appears in one place, it must disappear from another. If a process releases energy, it must have been stored somewhere beforehand. This logic allows scientists to reconstruct unseen causes from visible effects. In complex systems, this becomes a powerful investigative tool. In astrophysics, scientists infer invisible objects by tracking energy flows. The motion of stars reveals gravitational energy tied to unseen mass. In particle physics, missing energy signals the presence of particles that cannot be directly detected. The rule of conservation turns absence into evidence. Hidden energy also governs the arrow of time. While total energy remains constant, its organization changes. Energy naturally spreads from concentrated forms to dispersed ones. This tendency gives time its direction, distinguishing past from future. The conservation law does not oppose this trend, it allows it. Energy remains constant, but order decreases. Feynman's genius was in showing that none of this requires energy to be a physical substance. The rule works precisely because energy is abstract. It is flexible enough to include motion, heat, fields, mass, and vacuum fluctuations, yet strict enough to forbid imbalance. Its abstraction is what gives it universal reach. At the human scale, This understanding alters how we view progress and limitation. Every technological achievement is an exercise in energy transformation. Every limitation arises from how energy disperses. The universe does not deny energy, it denies perfect control over its forms. This is not a failure of physics, but a reflection of nature's structure. Ultimately, conservation of energy reveals a universe that is deeply consistent. Beneath all complexity, chaos, and change lies an unbreakable balance. Energy flows, hides, spreads, and transforms, but it never disappears. Feynman's explanation strips away illusion and replaces it with clarity. The universe keeps perfect accounts, even when we struggle to see where everything is stored. This insight leaves us with a quiet but powerful understanding. Every action, no matter how small, rearranges energy. Nothing happens without cost, and nothing is ever free. The books are always balanced, and the universe never forgets a single transaction. When Richard Feynman said that energy is not a thing but a number, he was deliberately overturning one of the most persistent intuitions people have about the physical world. Human thinking is shaped by objects. We understand stones, water, fire, and wind as things that exist independently and can be moved, stored, or consumed. Because energy causes motion, heat, and change, it feels natural to imagine it as another kind of substance flowing through reality. Feynman argued that this intuition, while understandable, is fundamentally wrong. Energy does not exist as an independent object. It has no shape, no color, no location by itself. You cannot point to energy in isolation. What you can do is describe a system and assign it a number that represents its energy. That number changes when the system changes, but the total number across all related systems remains constant. This idea sounds simple, yet it has profound implications for how we understand nature. Feynman emphasized that physics often advances not by discovering new things, but by discovering new ways of counting. Energy is one of the most successful counting schemes ever devised. It allows physicists to track change without needing to know every microscopic detail. Instead of following trillions of atoms individually, one can calculate energy before and after a process and know something deep must remain the same. Calling energy a number does not mean it is arbitrary. The number is not chosen freely. It is calculated according to strict rules derived from observation and experiment. Different physical situations require different formulas for energy, but once those formulas are established, the resulting number behaves with absolute consistency. No experiment has ever shown the total energy number to change unexpectedly. This numerical nature explains why energy can appear in so many disguises. Motion, heat, light, chemical reactions, electrical currents, and mass itself all correspond to different ways of calculating energy. They look nothing alike, yet they are unified by the fact that they contribute to the same total. The unification is not physical in appearance, it is mathematical in structure. Feynman wanted people to understand that asking, "What energy is made of?" is the wrong question. Energy is not made of anything. It is a property we assign to systems based on their state. A moving object has energy because of how fast it is moving. A raised object has energy because of its position relative to something else. A hot object has energy because its atoms are moving randomly. None of these energies exist independently of the systems involved. This becomes clearer when we consider that energy has no unique physical marker. You cannot detect energy with a single universal sensor. You detect motion, temperature, radiation, or force, and then infer energy through calculation. Energy is always one step removed from direct observation. It exists in the mathematics that connects observations, not in the observations themselves. Feynman often contrasted energy with quantities like mass or charge. Mass is something objects possess. Charge creates forces that can be measured directly. Energy, by contrast, is relational and contextual. Its value depends on reference frames, chosen 0 points, and system boundaries. The fact that energy can be shifted by choosing a different reference level shows clearly that it is not a physical substance. You can change the numerical value of potential energy without changing anything physical, simply by redefining where zero lies. Yet despite this flexibility, differences in energy matter deeply. While the absolute value of energy can change with conventions, changes in energy are physically meaningful and measurable. This again reinforces the idea that energy is about comparison and transformation, not substance. Physics cares about how energy changes, not where some absolute reservoir of energy is stored. This numerical viewpoint also explains why energy conservation is so powerful. Conservation does not say that a thing is preserved, it says that a calculation yields the same result before and after a process. Nature behaves as if it respects this accounting rule unfailingly. That reliability gives energy its central role in physics. Feynman highlighted that confusion arises when people mix metaphors. When energy is treated as a fluid, people ask where it flows or leaks. When treated as fuel, they ask where it is consumed. These metaphors can be useful in limited contexts, but they break down quickly. The numerical view avoids these traps. Numbers do not flow or leak, they change according to rules. In mechanics, energy is calculated from motion and position. In thermodynamics, it is calculated from temperature and microscopic motion. In electromagnetism, it is calculated from fields. In relativity, it includes mass. In quantum mechanics, it appears in discrete levels. Each theory provides a different recipe for calculating the same conserved number. The diversity of formulas does not undermine the concept, it confirms it. One of the most striking consequences of energy being a number is that it can be negative. Physical substances are rarely negative in any meaningful sense, but energy values can be. Gravitational systems often have negative energy relative to separated states. This makes sense numerically but would be absurd if energy were a physical material. Negative energy highlights again that energy is a bookkeeping concept, not a tangible object. Feynman also pointed out that energy being a number allows physics to tolerate ignorance. Scientists often do not know the detailed mechanism of a process, yet energy conservation still applies. This allows progress even when understanding is incomplete. If energy were a substance, ignorance of its nature would cripple prediction. Because it is a number, prediction remains possible. This perspective becomes especially important in modern physics, where intuition fails. In quantum mechanics, particles behave in ways that defy classical imagery. Trying to imagine energy as a thing in these contexts leads to contradiction. Treating it as a number preserves consistency. Energy levels, transitions, and probabilities all make sense mathematically, even when visualization breaks down. Feynman's insistence on clarity was not meant to remove wonder. On the contrary, recognizing energy as a number reveals a deeper wonder. The universe can be described, constrained, and understood through abstract relationships. Reality responds to mathematics with astonishing obedience. The fact that a numerical rule can govern everything from falling apples to exploding stars is deeply remarkable. This view also changes how we think about explanation itself. Explaining something does not always mean describing its substance. Sometimes it means identifying the invariant that persists through change. Energy is one of those invariants. It does not explain why things happen in a narrative sense, but it explains what must be true whenever they do. In everyday life, this insight remains hidden because language encourages substance-based thinking. We speak of oozing energy or having energy, which suggests possession. Scientifically, what we mean is that systems are changing state and redistributing energy numerically. The language is convenient, but the underlying reality is mathematical. Feynman's explanation ultimately invites a shift in perspective. Instead of asking where energy is, we ask how energy is calculated. Instead of asking what energy is made of, we ask how it changes. This shift aligns thinking with how nature actually behaves. By accepting energy as a number rather than a thing, confusion dissolves. Paradoxes become bookkeeping problems. Disappearances become transformations. The universe stops looking like a machine powered by mysterious fuel and starts looking like a system governed by unbreakable numerical relationships. This realization does not make energy less real, it makes it more fundamental. Energy's reality lies not in substance but in structure. It is a rule written into the fabric of change itself, and the universe obeys it with unwavering precision. Seeing energy as a number rather than a thing forces an even deeper shift in how we interpret physical processes. Once this idea is accepted, many long-standing puzzles dissolve, not because the universe becomes simpler, but because our questions become better aligned with how nature actually operates. Feynman emphasized that confusion arises when we demand physical imagery for concepts that are fundamentally abstract. Energy belongs to this category, and accepting that fact opens a clearer path to understanding. One of the most important consequences of energy being a number is that it does not need a physical carrier. Motion needs objects, heat needs particles, light needs fields, but energy itself needs none of these. It is assigned to whatever configuration exists. When that configuration changes, the number changes form. This is why energy can move instantly across a system, even when matter moves slowly. The number updates everywhere the system allows, constrained only by physical laws, not by the movement of a substance. This idea becomes strikingly clear in electromagnetic systems. When a circuit is completed, energy appears almost immediately in a distant bulb, even though electrons drift at a snail's pace. If energy were a substance attached to electrons, this would be impossible. Once energy is understood as a numerical property of the electromagnetic field configuration, the behavior becomes natural, the fields rearrange, and the energy calculation changes throughout the system. Feynman's insistence that energy is a number also explains why energy cannot be localized in a simple way. Asking, "Where is the energy right now?" often has no single answer. Energy may be partly in motion, partly in fields, partly in thermal vibrations, and partly in relationships between objects. The number belongs to the whole system, not to a single point. This non-local character is deeply uncomfortable for everyday thinking, but essential for accurate physics. This perspective also clarifies why energy values depend on reference choices. Potential energy, in particular, can be shifted up or down by redefining the zero level without changing any physical behavior. If energy were a substance, this would make no sense, but as a number used for comparison, it is perfectly reasonable. Only differences in energy affect motion and change, not absolute values. In quantum mechanics, the numerical nature of energy becomes unavoidable. Energy appears in discrete levels, like rungs on a ladder. Particles cannot possess arbitrary energy values, they can only occupy allowed numerical states. When they transition between these states, they absorb or emit precise amounts of energy. Trying to picture this process as energy, chunks, moving around leads to confusion. Treating it as changes in numerical states preserves clarity. Even stranger, quantum systems sometimes allow temporary violations of classical intuition. Energy can fluctuate briefly, provided the accounting balances over time. This does not mean the rule is broken. It means the rule is applied at a deeper statistical level. The number may waver locally, but globally and over time it remains consistent. This flexibility would be impossible if energy were a physical substance bound by rigid location and movement. Feynman also pointed out that treating energy as a number protects physics from false explanations. When people imagine energy as a mysterious force, they are tempted to use it as a placeholder for ignorance. Saying, "Energy causes this," explains nothing. Recognizing energy as an accounting tool forces scientists to look for actual mechanisms, forces, fields, interactions, while using energy only to track consistency. This discipline has been crucial in scientific progress. Energy conservation often reveals when a proposed explanation is incomplete. If the energy does not balance, something is missing. This missing piece may be an unknown particle, an unseen interaction, or a misunderstood process. In this way, energy accounting becomes a detective tool rather than an explanation in itself. The numerical nature of energy also explains why it unifies physics so effectively. Different theories describe different phenomena, but they all agree on energy conservation because they all rely on the same accounting structure. The details differ, but the bookkeeping remains compatible. This compatibility allows theories to connect rather than conflict. At a philosophical level, Feynman's explanation suggests that reality may be more mathematical than material. The deepest rules do not describe substances but relationships and constraints. Energy is one of those constraints. It limits what can happen without dictating how it must happen. Nature is creative within boundaries, and energy defines one of the most important boundaries. This view also reshapes how we think about explanation in everyday language. When we say someone has energy, we are describing a state of their body, chemical balances, temperature, motion, not a possession. When a machine uses energy, it is not consuming a substance but transforming numerical relationships. These phrases remain useful metaphors, but they should not be mistaken for literal descriptions. Feynman's approach encourages intellectual honesty. It admits that some fundamental concepts resist physical imagery. Rather than forcing misleading pictures, physics chooses abstraction. This choice has allowed it to describe phenomena far beyond human experience, from black holes to quantum fields. Ultimately, understanding energy as a number reveals a universe governed by consistency, rather than material bookkeeping. The universe does not shuffle energy around like coins, it maintains balance through transformations governed by precise rules. Every change respects this balance, whether or not we can visualize it. This realization leaves us with a powerful insight. The most reliable features of reality may not be things we can see, but patterns we can calculate. Energy is one of those patterns. It is not something the universe contains, it is something the universe obeys. The idea that energy transforms rather than being created or destroyed sits at the very heart of how Richard Feynman wanted people to understand nature. This principle is often summarized in a single sentence, yet its meaning is far deeper than the simplicity of the words suggests. It tells us that the universe does not generate energy out of nothing, nor does it allow energy to vanish. Instead, every event is a rearrangement, a reshaping, a redistribution of what already exists. Feynman emphasized that this principle removes drama from the universe in one sense, while adding a deeper kind of wonder. Explosions, fires, motion, life, and even thought feel dynamic and creative, as if something new is constantly being produced. Physics reveals a subtler truth. Nothing fundamentally new is created in these processes. What changes is the form, the organization, and the location of energy. Consider fire, one of humanity's oldest symbols of creation and destruction. When wood burns, flames leap upward, heat spreads, and light fills the air. It feels like energy is being released from the wood, as if it were stored inside as a substance. In reality, the chemical energy stored in molecular bonds is being transformed. Oxygen and carbon rearrange, and the difference in energy between the old bonds and the new ones appears as heat and light. The fire does not create energy. It converts energy that already existed in a different form. Feynman liked such examples because they strip away mystery without removing meaning. The beauty of fire remains, but the explanation becomes clearer. The universe is not inventing energy at the moment of combustion. It is following a rule of transformation that applies everywhere, from a campfire to the core of a star. Motion offers another powerful illustration. When a ball is thrown upward, it slows, stops, and falls back down. To everyday thinking, the energy of motion seems to disappear at the top and reappear on the way down. Physics shows that nothing vanishes. The energy transforms into gravitational potential energy, stored in the relationship between the ball and the earth. At the peak, the energy is fully transformed, not destroyed. As the ball falls, the transformation reverses. This constant shifting of form explains why energy often feels elusive. We expect continuity in appearance, but nature offers continuity in accounting, not in sensation. The universe does not promise that energy will remain visible, useful, or concentrated. It only promises that the total will remain balanced. Feynman also stressed that this principle applies even when transformations are complex or spread out. When a moving car slows to a stop, its kinetic energy transforms into heat in the brakes, tires, road, and surrounding air. The energy is not lost, it is scattered. Because it is scattered, it becomes harder to notice and harder to recover, but it remains fully present. This scattering introduces an important distinction between energy conservation and usefulness. While energy is always conserved, its ability to do organized work decreases as it spreads. This is why machines wear out and why waste heat accumulates. The universe does not destroy energy, but it allows energy to become increasingly disordered. Feynman was careful to point out that this does not contradict the transformation principle. Transformation includes degradation of usefulness. Energy can move from organized motion into random motion without violating conservation. The rule never promised convenience, only balance. In living systems, this transformation is continuous and intricate. The human body does not create energy. It transforms chemical energy from food into motion, heat, electrical signals, and biological repair. Even thought is an energetic process, involving electrical and chemical transformations in the brain. Life feels special, yet it follows the same rules as falling rocks and burning fuel. This realization removes the idea that life is exempt from physical law. Instead, it reveals that life is a highly sophisticated system of energy transformations, finely tuned but never breaking the rules. Feynman found this view more inspiring than any notion of exemption, because it connects living systems directly to the rest of the universe. At cosmic scales, the transformation principle becomes even more striking. Stars shine by transforming mass into energy. Nuclear fusion rearranges protons, and the slight loss of mass appears as radiant energy. This process can continue for billions of years, lighting entire galaxies. Yet even here, nothing is created from nothing. The energy was present in the mass all along, hidden in a form humans did not recognize until relativity revealed it. This discovery did not overthrow conservation of energy. It expanded the accounting system. Mass became another form energy could take. The principle of transformation remained untouched, demonstrating its extraordinary resilience. Feynman also emphasized that transformation applies even when processes seem irreversible. A shattered glass does not spontaneously reassemble. Heat does not flow from cold to hot on its own. These facts might suggest energy loss, but they do not. They reflect the tendency of energy to spread, not to disappear. The accounting still balances perfectly. Understanding transformation rather than creation changes how we think about resources. When fuel is burned, energy is not destroyed. It is transformed into heat and dispersed into the environment. The problem is not energy loss, but loss of concentration. This insight lies behind modern discussions of efficiency and sustainability. Feynman's explanation also guards against false hope. Claims of free energy or perpetual motion promise creation without cost. Physics responds calmly. Such devices fail because they demand violation of transformation rules. Energy cannot appear without transformation, and transformation always requires something to change elsewhere. Ultimately, the idea that energy transforms rather than being created or destroyed reveals a universe that is honest and consistent. Every effect has a source, every release has a prior storage, nothing comes from nowhere, and nothing vanishes without trace. This principle reshapes our sense of change itself. Change is not invention, it is rearrangement. The universe is not a factory producing energy, nor a sink absorbing it. It is a vast system of continuous transformation, endlessly reshaping what already exists while never altering the total balance. Richard Feynman believed that the most powerful way to understand deep physics was not through abstract equations alone, but through ordinary experiences that quietly reveal universal laws. When he spoke about energy, he often returned to simple, everyday situations because they expose the truth without decoration. Energy is not reserved for laboratories or cosmic events. It is present in every step we take, every sound we hear, and every object we touch. A child running across a playground offers a complete lesson in energy. As the child runs, chemical energy stored in food is transformed into motion and heat. Muscles contract, bones move, and the body warms. When the child stops, the motion disappears, but the energy does not. it has become heat in the body and the surrounding air. Nothing mysterious occurs, yet the transformation is total and exact. Feynman emphasized such examples because they challenge the idea that energy is something exotic. The laws governing nuclear reactions also govern walking, breathing, and speaking. Everyday life is a continuous demonstration of energy conservation and transformation, even though we rarely think of it that way. Sound is another familiar example. When a bell rings, it fills the air with vibrations. These vibrations carry energy, even though air molecules barely move from their positions. They oscillate, passing the disturbance along. As the sound fades, the energy does not vanish, it dissolves into tiny, random motions of molecules becoming heat. The ringing stops, but the accounting remains perfect. Light provides an equally revealing example. A lamp converts electrical energy into light and heat. The light travels through space, carrying energy until it strikes an object. When absorbed, the light's energy becomes heat or triggers chemical reactions, such as those that allow vision. The light disappears, but its energy continues in a new form. Feynman loved these examples because they show that energy is never confined to one dramatic moment. It flows quietly through ordinary events. When we open a door, energy moves from muscles to hinges. When we write, energy moves from the brain to the hand to the page. Each action is small, but each obeys the same rules as the largest events in the universe. Falling objects offer another everyday illustration. When something is lifted, energy is stored in its position relative to the earth. When it falls, that stored energy becomes motion. If it hits the ground, the motion becomes heat, sound, and deformation. The entire sequence unfolds without loss, only transformation. Even sitting still involves energy. The body constantly converts chemical energy into heat to maintain temperature and sustain life processes. The absence of visible motion does not mean the absence of energy. It means energy is transforming in ways we cannot easily see. Feynman's use of everyday examples serves a deeper purpose. It reveals that energy is not an abstract invention detached from reality. It is woven into experience itself. The same accounting rule applies whether we notice it or not. This realization changes how we interpret effort and fatigue. Feeling tired does not mean energy has vanished. It means the body has transformed stored energy into heat and less organized forms that are harder to reuse. Rest and food restore organized chemical energy, allowing transformation to continue. Everyday examples also clarify why energy efficiency matters. When a machine produces excess heat, it is not losing energy but converting it into a form less useful for the task. Understanding this distinction helps explain why no machine can be perfectly efficient and why design focuses on managing energy transformation rather than preventing energy loss. By grounding physics in daily experience, Feynman showed that understanding energy is not about memorizing definitions. It is about seeing the hidden continuity beneath change. Ordinary life becomes a quiet demonstration of universal law, and the abstract idea of energy gains meaning through familiarity. In the end, everyday examples do more than illustrate energy. They remind us that the universe operates by the same rules at all scales. The laws shaping stars and atoms are the same laws shaping footsteps and voices. Energy is not distant or mysterious. It is present in every ordinary moment, transforming silently and faithfully, never created, never destroyed, always accounted for. Energy does not belong to a single scale of reality. One of the most powerful insights Richard Feynman emphasized is that the same idea of energy applies seamlessly from the smallest building blocks of matter to the largest structures in the universe. This continuity across scales is not obvious at first, because the form's energy takes change dramatically. Yet the underlying accounting never breaks, no matter how small or how vast the system. At the atomic scale, energy behaves in ways that challenge everyday intuition. Atoms do not absorb or release energy smoothly. Instead, they do so in precise amounts. Electrons occupy specific energy levels, and transitions between these levels involve exact quantities of energy. This quantization explains why atoms emit light of specific colors and why chemical reactions follow predictable patterns. Even though the behavior looks strange, the energy balance remains exact. Feynman pointed out that these atomic rules are not special exceptions. They are simply the form energy takes when systems become very small. The numerical nature of energy becomes especially clear here. Energy is no longer something we can imagine flowing continuously. It jumps between allowed values. Yet the total accounting still holds. Moving up in scale, molecules store energy in bonds and vibrations. When molecules interact, energy shifts between chemical bonds, motion, and heat. A reaction may release energy, appear calm, or absorb energy, but in every case, the balance remains intact. The complexity of chemistry does not weaken the principle, it demonstrates its adaptability. At the human scale, energy appears familiar. Motion, heat, sound, and light dominate experience. Machines convert fuel into work. Bodies convert food into movement and warmth. Even here, the same energy rules govern behavior. Nothing new is added, and nothing is lost. The apparent simplicity of everyday energy hides the same principles that operate at smaller scales. Feynman stressed that what changes across scales is not the rule, but the way energy is stored and transferred. Atoms rely on quantum rules. Machines rely on classical mechanics. Stars rely on nuclear processes. Yet each system uses energy accounting appropriate to its scale. At the scale of stars, energy becomes overwhelming in magnitude, but not in principle. Stars shine because nuclear fusion transforms mass into radiant energy. The energy travels outward as light, warming planets and driving chemical reactions. This energy has the same status as any other form. It is counted, conserved, and transformed. Galaxies offer another perspective. Their structure and motion depend on energy stored in gravitational relationships. Stars orbit galactic centers, held together by energy balances that shape cosmic evolution. Even when matter is invisible, energy accounting reveals its presence. At the scale of the universe itself, energy influences expansion and fate. The distribution of energy in matter, radiation, and space determines how the universe evolves over billions of years. Despite the scale, the same principle holds: energy is never destroyed. Feynman found this universality deeply satisfying. It suggests that the universe is not a patchwork of unrelated rules, but a coherent whole. The same idea that explains a vibrating atom also explains a shining star. This continuity across scales teaches an important lesson about understanding reality. Differences in appearance do not imply differences in principle. Energy changes its expression, not its behavior. From atoms to galaxies, energy acts as a unifying thread, linking the smallest motions to the grandest structures. It is a quiet consistency running through all of nature, reminding us that the universe, in all its diversity, obeys a single, unbroken rule. Understanding energy in the way Richard Feynman explained it does more than clarify a scientific concept. It changes how we interpret reality itself. Energy stops being a mysterious substance or a poetic force and becomes a guiding principle that reshapes our view of cause, change, and limitation. Once this perspective is adopted, the universe appears less chaotic and more deeply structured, governed by balances that never fail. Feynman's explanation encourages a shift away from surface appearances. When something dramatic happens, an explosion, a collapse, a burst of light, it feels like a moment of creation or destruction. Energy accounting reveals a calmer truth. Nothing truly begins or ends in these events. What changes is arrangement. The universe is not constantly inventing new power, it is continuously rearranging what already exists. This realization brings clarity to many common misunderstandings. When people speak of running out of energy, they are usually referring to running out of organized, useful energy. The total energy remains, but it has become scattered, harder to concentrate, and more difficult to direct. Recognizing this distinction changes how we think about efficiency, waste, and sustainability. The challenge is not conserving energy in the absolute sense, but managing its forms. Seeing energy as a rule rather than a thing also sharpens critical thinking. It prevents the misuse of energy as a vague explanation. Saying that energy caused something explains nothing by itself. Feynman insisted that real explanations must identify forces, interactions, and mechanisms. Energy accounting then checks whether those explanations are complete. If the numbers do not balance, something is missing. This approach has profound implications for scientific discovery. Many breakthroughs have come from noticing missing energy. When experiments fail to account for all the energy, scientists know they have overlooked something. Invisible particles, hidden interactions, or new forms of matter often reveal themselves through energy imbalance. In this way, energy becomes a guide toward deeper understanding rather than an endpoint. The perspective also influences how we think about limits. Energy conservation sets boundaries on what is possible. It explains why perpetual motion machines cannot exist and why there is no such thing as free energy. These limits are not technological failures, but reflections of how the universe works. Accepting them leads to more realistic goals and more honest science. On a personal level, this understanding encourages humility. Humans do not control energy, they work within its rules. Every action has a cost. Every gain requires a transformation somewhere else. This does not make progress impossible, but it ensures that progress is never free. Feynman's explanation also connects science to philosophy without drifting into abstraction. It suggests that the deepest truths about the universe may not be tangible objects, but invariant relationships. Energy is one such invariant. It survives every theoretical revolution, adapting its form while preserving its role. This stability gives science its confidence. Even as models change and theories evolve, energy conservation remains untouched. It is not fragile. It does not depend on fashion or interpretation. It is a rule the universe enforces relentlessly. Ultimately, understanding energy in this way changes how we see ourselves. We are not separate from the physical world, using energy from outside it. We are part of the same continuous transformation. Our bodies, technologies, and societies are expressions of energy rearranging itself according to unbreakable rules. This perspective does not diminish meaning, it deepens it. It reveals a universe that is honest, balanced, and profoundly consistent. Energy becomes not a mystery to be feared or romanticized, but a quiet truth that connects every process into a single, coherent whole. By seeing energy as Feynman did, we gain more than scientific insight. We gain a way of thinking that values clarity over illusion, balance over excess, and understanding over assumption. The universe may be complex, but it is not arbitrary. Energy ensures that, beneath all change, order remains.